22 watts. That is how much power Voyager 1 uses to talk to us. 22 watts. The light bulb inside your refrigerator uses about the same. Now take that refrigerator bulb and move it 25 billion kilometers away. Move it past Mars, past Jupiter, past Saturn, past Neptune, past Pluto, past the edge of the solar wind, past the boundary where our sun's influence ends and the cold emptiness between the stars begins. Put it there, in the dark, in the silence, and then try to see it from Earth. That is what NASA does every single day. And they do not just see it, they read data from it, they send commands to it, they have conversations with it, conversations that take 46 hours to complete, because even light, the fastest thing in the universe, needs 23 hours to travel from here to there, and 23 hours to bring the answer back. That is the reality of Voyager 1. The most distant human-made object in existence. A machine that has been running since 1977, a machine that has outlived the careers of every engineer who built it. A machine that is right now, at this very moment, sending us information about a place no human has ever been and no human will reach for thousands of years, but in October 2024, that machine went quiet. And for a few terrible days, the people at the Jet Propulsion Laboratory in Pasadena, California, thought they might have heard its voice for the last time. Here is what happened. On October 16, 2024, engineers at JPL sent a routine command to Voyager 1. They wanted to turn on one of its heaters. This was nothing unusual. They had been managing Voyager's dwindling power supply for years, carefully turning systems on and off to keep the spacecraft alive, but this time, the command triggered something unexpected. Voyager's fault protection system activated. This is an automated safety protocol that was written into the spacecraft's software back in the 1970s by engineers who knew they would not be around to troubleshoot problems decades later. When the fault protection system detects something it considers dangerous, it takes action on its own. It does not ask for permission, it does not wait for instructions from Earth, it just acts. And what it did was shut down the main radio transmitter. Voyager 1 has two radio transmitters. The primary one operates on what is called the X-band frequency, between 8 and 12 gigahertz. This is the transmitter that Voyager has been using to talk to Earth for decades. It produces a relatively strong signal that NASA's Deep Space Network can detect across billions of kilometers. The backup transmitter operates on the S-band frequency, between 2 and 4 gigahertz. It uses less power, but its signal is much fainter. The last time Voyager used the S-band transmitter was in 1981, 43 years ago. On October 18th, 2 days after the heater command was sent, engineers tried to listen for Voyager's response. They pointed the giant dishes of the Deep Space Network at the exact spot in the sky where Voyager should be and listened on the X-band frequency. Nothing, just static, the cosmic background noise of the universe. No spike, no carrier wave, no Voyager. At first they thought the signal might just be weaker than expected. The fault protection system had lowered the data transmission rate to conserve power, which changed the characteristics of the signal. Engineers began sifting through the data more carefully, looking for anything that matched Voyager's known transmission pattern. And they found it, a faint signal. Barely there, but present, Voyager was still transmitting on X-band, just at a lower rate. But then, on October 19th, it stopped completely. The fault protection system triggered again, and this time, it did something that nobody at NASA was sure would work. It switched to the backup S-band transmitter, the one that had been sitting dormant inside the spacecraft for 43 years. A piece of 1970s electronics that had been powered off since the Reagan administration, floating through the vacuum of space, subjected to cosmic rays and extreme temperature swings for over 4 decades. And it turned on. Voyager, alone in the dark, with no human guidance, autonomously switched to a backup system that its creators had included just in case. And it started transmitting. The question was whether anyone on Earth could hear it. The S-band signal is significantly weaker than the X-band signal, and Voyager is much farther away now than it was in 1981 when the S-band was last used. Back then, Voyager was near Saturn, roughly 1.5 billion kilometers from Earth. Now it is more than 25 billion kilometers away. The signal has to travel nearly 17 times farther, and signal strength drops off with the square of the distance. That means the signal reaching Earth would be roughly 300 times weaker than what the S-band delivered from Saturn's neighborhood. But the Deep Space Network engineers found it. They tuned their massive dishes to the S-band frequency and detected Voyager's carrier wave, a thin ghostly spike rising just barely above the noise floor. It was not enough to carry data, the signal was too faint for that, but it was enough to confirm one critical thing. Voyager 1 was still alive, still pointed at Earth, still trying to talk. And it was not just NASA, the camera's radio astronomy group in the Netherlands, using the Dwingeloo telescope, also detected the signal. This telescope was not even designed for the frequency Voyager was transmitting on. They had to mount a new antenna to pick up the 8.4 GHz X-band signal, and despite the telescope being far smaller than NASA's 70-meter dishes, they found it. They used orbital predictions to correct for the Doppler shift caused by the relative motion of Earth and Voyager, and there it was, a narrow spike drifting slowly in frequency, exactly as expected for a transmitter accelerating away from Earth at 17 kilometers per second. The Allen Telescope Array, a collection of 42 smaller dishes in Northern California operated by the SETI Institute, also detected the carrier wave. They measured a carrier-to-noise ratio of about 11.5 decibels, not strong by any standard, but unmistakably Voyager. Think about what this means from an engineering perspective. A signal transmitted with 22 watts of power from 25 billion kilometers away was detected by dishes on Earth. The power of that signal when it reaches our antennas is measured in units called attawatts. 1 attawatt is 1/1000th of 1/1000th of a watt. That is 0.00000000000000000001 watts. To put that in perspective, the energy hitting the antenna from Voyager is about 20 billion times weaker than the signal from a typical cell phone tower. It is weaker than the thermal noise generated by the electronics in the receiver itself. Finding it requires knowing exactly where to look, exactly what frequency to listen on, and exactly how the signal should be drifting due to the Doppler effect. It is like trying to hear one specific person whispering in a stadium full of people screaming, except the stadium is the entire universe. And the universe is loud. The sun emits radio waves across a broad spectrum. Jupiter produces powerful radio bursts from its magnetosphere. Pulsars spin and sweep their radio beams across the sky like cosmic lighthouses. Quasars, powered by supermassive black holes billions of light-years away, produce a constant background hum of radio noise. The cosmic microwave background, the afterglow of the Big Bang itself, fills every direction of the sky with faint microwave radiation. All of this noise lands on the antenna at the same time as Voyager's signal. The way engineers extract Voyager's voice from this chaos is remarkable. They know the exact frequency Voyager should be transmitting on, but that frequency is not fixed. Because Voyager is moving away from Earth at about 17 kilometers per second, the received frequency is shifted lower by the Doppler effect. And because Earth is rotating and orbiting the Sun, the Doppler shift changes continuously throughout the day. Engineers calculate this changing frequency in advance, down to fractions of a hertz, and tune the receiver to follow it. This is called Doppler tracking. It turns the search from looking for a needle in a haystack to looking for a needle in a very specific, very narrow slice of the haystack. Then they integrate the signal over time. By recording data for hours and adding up the received energy at the predicted frequency, they can pull the signal above the noise. The longer they listen, the better the signal stands out. It is the radio equivalent of taking a long exposure photograph in the dark. Individual photons are invisible, but if you collect enough of them, the image appears. The reason this is possible comes down to a simple but brilliant concept. A dish antenna does not just collect radio waves, it focuses them. The 70-meter dish at Canberra, Deep Space Station 43, has a collecting area of nearly 4,000 square meters. All the radio energy falling on that enormous surface gets concentrated onto a small receiver at the focus point. It is the same principle as using a magnifying glass to focus sunlight onto a point. And the receiver itself is cooled to just a few degrees above absolute zero using liquid helium. This reduces the thermal noise to almost nothing, making even the faintest signals stand out. Now here is the other part of this story that most people do not appreciate. The reason Voyager's signal can still reach us is not just about the antenna on Earth, it is about the antenna on Voyager. The spacecraft carries a 3.7-meter high-gain dish antenna. This antenna focuses the transmitted signal into a narrow beam pointed directly at Earth. If the antenna drifts out of alignment even slightly, the signal misses Earth entirely and disappears into empty space. Keeping that antenna pointed at Earth requires thrusters, small bursts of hydrazine fuel that nudge the spacecraft to maintain its orientation. But the fuel lines to some of those thrusters have been clogging for years. A residue has been building up inside the fuel tubes, restricting the flow of hydrazine. If the thrusters stop working, the antenna drifts and Voyager goes silent. Not because it stopped transmitting, but because the beam is no longer aimed at us. This is why, in March 2025, NASA engineers pulled off another miracle. They revived a set of backup roll thrusters that had been considered dead since 2004. 21 years, these thrusters had been unused. The engineering team at JPL figured out that the original diagnosis of failure might have been wrong. One engineer had an insight that the problem could have a different cause and might be fixable. They sent commands to test the thrusters, commands that would take 23 hours to reach Voyager, then they waited another 23 hours for the response. If the test failed, Voyager could already have been in trouble before they even knew, but within 20 minutes of receiving the data back, they saw the thruster heater temperatures rising. The thrusters worked. This fix was urgent because of another looming problem. Deep Space Station 43, the only antenna on Earth powerful enough to send commands to Voyager, was scheduled to go offline for major upgrades starting May 4, 2025. The antenna would be down for months, with only brief windows of operation in August and December. The upgrades are needed to support future crewed lunar missions, but in the meantime, it meant no one could talk to Voyager. They could listen, but they could not send commands. If something went wrong during those months, there would be no way to fix it. The thruster revival had to happen before that deadline. And it did, barely. Now let us talk about the power situation, because this is ultimately what determines how much longer Voyager can survive. Voyager does not have solar panels. At 25 billion kilometers from the sun, solar panels would be useless. The sunlight out there is too dim to generate any meaningful electricity. Instead, Voyager is powered by 3 radioisotope thermoelectric generators. These are devices that convert the heat from radioactive decay into electricity. Each RTG contains a sphere of plutonium-238. As the plutonium atoms decay, they release heat. Thermocouples surrounding the plutonium sphere convert that heat directly into electrical current through a principle called the Seebeck effect. When Voyager launched in 1977, its RTGs produced about 470 watts of electrical power. That was enough to run everything: the cameras, the spectrometers, the plasma detectors, the magnetometers, the heaters that kept the electronics warm enough to function, the radio transmitter, everything. To put 470 watts in perspective, that is less than the power consumed by a typical household hairdryer. Voyager explored Jupiter, Saturn, and their moons, took thousands of photographs, made some of the most important discoveries in planetary science, and transmitted all of that data back to Earth, all on less power than it takes to dry your hair. The efficiency of 1970s engineering is staggering when you think about it in those terms. But plutonium-238 has a half-life of 87.7 years. That means every 87.7 years, half of the remaining plutonium has decayed and the heat output drops by half. In practical terms, Voyager loses about 4 watts of power every year. By 2025, the available power had dropped to less than 200 watts, and it continues to fall. NASA has been managing this decline with agonizing precision. Over the years, they have shut down instrument after instrument. The cameras were turned off in 1990 after Voyager took its famous pale blue dot photograph of Earth from 6 billion kilometers away. The ultraviolet spectrometer was turned off, the photopolarimeter was turned off, heaters for the remaining instruments were turned off one by one, each time hoping the instrument would survive the cold. Some did, some did not. As of 2025, only 4 science instruments remain powered on: the cosmic ray detector, the low-energy charged particle detector, the magnetometer, and the plasma wave subsystem. These are the instruments that study the interstellar medium, the thin soup of particles and magnetic fields that fills the space between the stars. They are returning data that no other instrument in human history has ever collected, and what they have found is genuinely surprising. Before Voyager crossed the heliopause in August 2012, scientists had models and theories about what interstellar space would be like. Those models turned out to be partially wrong. The boundary between the solar system and interstellar space was not the clean, sharp line that many expected. It was messy, turbulent, and layered. Voyager found a region NASA called the heliosheath, where the solar wind slows down and piles up against the incoming pressure of interstellar particles. The magnetic field direction changed, the density of charged particles shifted, and even after crossing the heliopause, Voyager continued to detect pressure waves from the Sun, coronal mass ejections that rippled outward through the interstellar medium like waves spreading across a pond after a stone is dropped. In 2021, Voyager 1 detected a faint hum in the interstellar plasma, a persistent low-frequency vibration in the tenuous gas between the stars. This was the first direct detection of the ambient sound of interstellar space. It is unimaginably faint. The density of particles out there is so low that there is roughly 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains about 25 billion molecules per cubic centimeter. Interstellar space is essentially a vacuum, but it is not perfectly empty, and Voyager can hear it breathing, but the power continues to drop. NASA estimates that by 2027 or 2028, they will need to shut down more instruments. By the early 2030s, there may not be enough power to keep even the radio transmitter running. When that happens, Voyager will fall silent for the last time. Not because it broke, not because something went wrong, but because the physics of radioactive decay finally caught up. The spacecraft itself will keep moving. There is nothing in space to slow it down, no air resistance, no friction. At 61,000 kilometers per hour, Voyager will continue traveling through interstellar space indefinitely. In about 300 years, it will reach the inner edge of the Oort cloud, the vast shell of icy objects that surrounds the solar system at enormous distances. It will take about 30,000 years to pass through the Oort cloud. In roughly 40,000 years, it will pass within 1.6 light-years of Gliese 445, a small star in the constellation Camilla Pardalis. It will not stop there. It will continue orbiting the center of the Milky Way galaxy, essentially forever. But we will not know any of this, because by then, the radio will be dead. The golden record will still be attached to the spacecraft, carrying greetings in 55 languages, sounds of Earth, music from Beethoven to Chuck Berry, images encoded in analog format, but there will be no signal to announce its presence. It will be a message in a bottle, drifting through an ocean with no shore. The golden record itself is an extraordinary object. It is a 12-inch gold-plated copper disc. On its cover, there are instructions, written in the universal language of mathematics and physics, explaining how to play it. A diagram showing the position of our Sun relative to 14 pulsars, so that anyone who finds it can figure out where it came from. A map of the solar system showing which planet launched the spacecraft, and a representation of hydrogen atoms, the most common element in the universe, providing a basic unit of time and length. On the record itself, there are 115 images encoded as audio signals. Photos of Earth, of human anatomy, of animals, of cities, of mathematical equations, of the structure of DNA. There are greetings spoken in 55 languages, from ancient Sumerian to modern Mandarin. There is the sound of rain, the sound of thunder, the sound of a mother's first words to her newborn child. There is music, Bach's Brandenburg Concerto, Mozart's Magic Flute, a Navajo night chant, a Peruvian wedding song, Chuck Berry's Johnny B. Goodin. The record was curated by a committee led by Carl Sagan, who said that the spacecraft will be encountered and the record played only if there are advanced civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. It was also Carl Sagan who, in 1990, convinced NASA to turn Voyager 1's cameras around one last time before they were shut off forever. The result was the pale blue dot photograph. From 6 billion kilometers away, Earth appeared as a tiny speck of light, less than a pixel wide, suspended in a beam of scattered sunlight. Sagan wrote about that image with words that became among the most famous in the history of science. "Look again at that dot," he wrote. "That is here. That is home. That is us." The cameras were shut down shortly after that photograph was taken. The power they consumed was needed elsewhere. Voyager has been blind ever since. But it has not been deaf. It has continued listening to the universe with its remaining instruments, measuring the magnetic fields and particle densities of a realm no human sensor has ever reached. What strikes me about this story is not the technology, impressive as it is. What strikes me is the stubbornness. Voyager was designed in the 1970s. The computers on board have less processing power than a modern digital watch. The flight data subsystem has about 68 kilobytes of memory. Your smartphone has roughly 1,000,000 times more. The software was written by engineers who programmed in assembly language and stored code on magnetic tape. And yet these systems continue to function, nearly 5 decades later, in conditions that were never anticipated and were never tested for. The October 2024 S-band switch was not even the first crisis that year. In December 2023, Voyager 1 started sending back complete gibberish. The science data, the engineering telemetry, all of it was garbled, nonsensical patterns, repeating over and over. It took NASA 5 months to diagnose the problem. A single chip in the flight data subsystem had failed. One chip, out of the thousands on board, had been corrupted, probably by a cosmic ray hit. The engineers had to figure out which chip it was, then redistribute its functions across other parts of the computer's memory, all through commands that took 2 days for a round trip. They could not reboot the system, they could not swap the chip, they had to perform surgery on a computer from 25 billion kilometers away, using tools designed before the invention of the personal computer. And they fixed it. By mid-24, Voyager was sending clean data again. When the fault protection system switched to the S-band transmitter in October 2024, it executed a procedure that was written before most of the people currently working on the mission were born. That code sat dormant for 43 years, and then, when it was needed, it worked perfectly. Somebody in the 1970s thought about this scenario. Somebody said, what if the main radio fails? And somebody else wrote a few lines of code to handle it. And those lines of code just saved the mission. In July 2025, Voyager 1 resumed transmitting readable scientific data. The information it sent back included measurements of slight oscillations in the density of the interstellar plasma, basically the weather report from between the stars. No one else has this data. No other instrument on Earth or in space can measure what Voyager is measuring. It is telling us what the space between star systems actually looks like, not in theory, not in simulations, but in direct measurement. And every bit of that data travels 25 billion kilometers across the void, carried by a radio signal weaker than a firefly, collected by giant metal ears pointed at the emptiest part of the sky, processed by engineers who treat every byte like a treasure. There will come a day when the signal stops, when the last watt of power drains from the RTGs and the transmitter goes cold, when the antenna drifts and the beam sweeps past Earth for the final time. The monitors at JPL will show nothing but noise, and Voyager will continue on, silent, dark, frozen, carrying our golden record through the galaxy like a ghost ship on an infinite ocean. But that day is not today. Today, right now, if you had a big enough antenna and you pointed it at exactly the right spot in the sky, and you tuned to exactly the right frequency, and you waited long enough, and you filtered out the screaming of the cosmos, you would see it. A tiny spike, a barely visible bump in the noise, a 22-watt whisper from the edge of forever. That is Voyager 1, still talking, still out there, still ours. And somewhere on that spacecraft, etched into a golden disk that will outlast every monument and every civilization on Earth, there is a message. In the words of then-President Jimmy Carter, inscribed as part of the Golden Record package, this is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. 48 years later, the machine carrying those words is still trying. And so are the people listening for it.